Okay, welcome back to part two. So when you graph that on the calculator, you should have had a graph looking something like this, and they should have plotted one on top of another. So let's just quickly go there. So your graph should have looked like that. Okay, which means it's probably an identity. Okay, but to check for sure that it is an identity, we need to actually prove it. Okay, which is what we're going to do in part C here. So our left side of the equation was 1 over cos x minus cos x, and our right side was, I want to say sin x tan x. Would I be right? Yes, I would. Okay, good guess. Okay, sin x tan x. I have a good memory. It just only lasts about 2 seconds. Okay, so let's see here. Let's use our strategies. So we have a left side, we have a right side. Which side do you think looks more difficult? I would say left side we want to start with. We can work on both sides if we need to, but left side we have more opportunity to simplify because we have a fraction plus a whole number. Okay, so first step we is simplify. So there's no expanding, there's no brackets or anything. There's no factoring because can't really factor out anything from these two terms. We do have fractions, and we have like a fraction like 1 over cos plus, let's change this to a fraction, minus cos over 1. So we're going to get a common denominator for this. Okay, so each of these are going to be over top of cos x. I don't know why I switched to red. Let's change that back. And hopefully you guys like blue because that seems to be my favorite color. All right, so what we did here to get a common denominator is this one here, we ended up multiplying top and bottom by cos x. Okay, so that would make this, well, this one stayed the same. The second fraction would have been cos times cos, which would be cos squared. Now, make sure you're putting that 2 on the cos, not the x, okay? They are two different things. Cos of x squared, that means that's basically cos x times x, right? Cos squared x means cos x times cos x, okay? So two different things. You want to put the square on the cos in this case. All right, let's join them up so they're over top of 1. Particular cos here, so 1 minus cos squared over cos x. Okay, step 2, look for squared identities. Okay, this one's screaming at me. Do you guys remember what 1 minus cos squared is? If we manipulate our Pythagorean identity on my formula sheet, you would get, that's right, sine squared x. And then we still have cos x on the bottom. Okay, now if you want, we can stop there and work on the right-hand side. Or, well, I'll show you in a second. Let's say we work on the right-hand side. Okay, so tan x, we know tan x to be sine x over cos x, right? So what do we do when we're multiplying fractions? We would, first of all, put the whole number, the sine x, over top of 1. And then when we multiply fractions, we multiply the numerators. Sine times sine would be sine squared x, and 1 times cos, cos x. Ta-da! They're equal, yay! Left side equals right side, QED, which means thus it is proven. Or you can just put Yahoo, my personal favorite, okay? So we've shown that this is actually an identity. Okay, I had mentioned before you could just work on the left-hand side. I'm just going to show you in a different color how you would do that. You would break sine x up into sine squared x into sine x, like this. And then because these are multiplied together on top, you could combine sine x over cos x like that. Can't do that if that's adding, but you can if it's multiplying. So sine x over cos x would be tan x. So that's how you could just work on the left-hand side if you wanted. Okay, state the restrictions in terms of x. Okay, so we need to do our NPVs on this one. So take a look at your identity. We have 1 over cos minus cos, and then sine x tan x. So let's do the obvious ones where there's dividing going on. Okay, so see how we have cos x on the bottom? That right there tells us we need to write that cos x can't equal 0. Okay, otherwise you'd be dividing by 0. Then you look for your sneaky restrictions, okay? The sneaky one here is tan. Okay, now tan is actually sine over cos. So again, cos x can't equal 0. You don't have to write it twice, okay? We've covered it already. All right, so where is cos equal to 0? Well, that would be where x is 0, so that would be here and here. And for some reason, they usually do these in radians, so we would call this first angle pi over 2. Now, these two angles are the same distance apart, so we could just simply add multiples of pi, so pi n, where n is an element of the integers, to come up with our general solution restriction. And there you go. All right. Example number 2, prove the identity sine x cos squared plus sine cubed equals 1 over cosecant x. Algebraically, okay? So what they mean there is don't put it in your graphing calculator. If you want to check it that way, that's fine, but no need to check it really. And then determine the non-permissive values. Okay, let's write left side on this side. Plus sine cubed x. Whoa, I should have started further over. And then 1 over cosecant x on the right side. Okay, let's use our strategies here. So you've got that strategy sheet next to you here, and you're looking at it right now. First step, simplify. Oh, first step, start with the more difficult looking side. So again, I think left side wins that one. Okay, step 1, we're going to either factor, expand, or play with fractions. So we have no fractions, so we can get rid of those right away. There's no multiplying to do, so no expanding, but we do have factoring to do. If you take a look at this, this is one term, and that's another term separated by plus signs. They have a common factor. What do they have in common? That's right, sine x. Okay, so if we factor sine x out from the first term, that would leave cosine squared x, so we're dividing sine x out, plus sine cubed x divided by sine x would be sine squared x. Okay, so we factored sine x out. Okay, step 2, look for squared identities. Ah, this one is screaming at me. Cos squared plus sine squared on your formula sheet under Pythagorean identities. Well, it doesn't say Pythagorean identities, but it's under the squared parts. That equals 1. And there we go. We have, therefore, sine x times 1, so sine x. All right, well, let's take a look at the right-hand side, 1 over cosecant x. Okay, so here's the deal. We could change sine x on the left side here to 1 over cosecant x, because we know that cosecant x is equal to 1 over sine. So therefore, if you reciprocal both sides, 1 over cosecant x should equal, flip this, sine x. Okay, so we could do that. And yay, Yahoo! It is proven. All right, now non-permissible values. Okay, let's start with the obvious ones. Do we have any dividing going on? Yes, we do, right here. The cosecant x is on the bottom. So cosecant x can't equal 0. Do we have any sneaky ones? Not on the left side, but on the right side. I know this is on the bottom, but actually cosecant is 1 over sine, right? So we also would say sine x can't equal 0. Okay, so cosecant is actually 1 over sine, can't equal 0. So if we have 1 divided by anything really besides 0, that really will never equal 0. So we have no NPVs from this particular branch, okay? So we don't have to worry about that. This one, however, where sine is 0, okay, sine is y would be 0 here and here. So start with your first positive angle, which would be 0, plus, again, these are the same distance apart, pi apart, so plus pi n, where n is an element of the integers. And if you wanted to clean that up a little bit, you could get rid of the 0, okay? You could just write pi n. Okay, that's a little more simple if I can get rid of that negative sign. There we go. There's our non-permissible values. Yay. Okay, let's look at the next page. Okay, well, example 3 is another proof. Okay, so let's do left side, right side over here, 1 over cotan A. Okay, left side definitely looks more complicated. So I guess we'll be beginning with that side. And you know what? I'm just thinking we might want to start a little bit further over. Let's move that over just a bit more. So sine A plus tan A, you never know, sometimes these take a while, over 1 plus cosine A. Okay, so think of your strategies. Factor, nope, there's no factoring on top or the bottom. Expand, no, there's no multiplying out. We do have a fraction, but it's already one fraction. We do have 1 minus cos. We could multiply top and bottom by 1 minus cos squared. Let's see, is that going to make the top look better? I'm not sure it will, actually. I think it'll make the top look worse when we multiply out 1 minus cos with this. So yeah, that's not going to be good. Okay, so we really have nothing from step 1. Step 2, look for squared identities. Nope, I don't see anything squared. Step 3, change everything in terms of sine and cos. So we're down to our last resort. Tan, we're changing to sine A over cos A using that formula on your formula sheet. Oh, you know that one already anyways, so. Okay, and then 1 plus cos A still on the bottom. All right, everything's in terms of sine and cos. Let's multiply. Here's how we're going to get rid of the little fraction within the big fraction. We're going to multiply the top and the bottom by your lowest common denominator of that little fraction. And you can do this because really then you're only just multiplying by cos A over cos A, which essentially equals 1. We're not changing the value. Okay, now when we do this, we need to multiply it through to both terms. Although on the bottom, I would actually keep it the way it is. Don't multiply it through. It's just on top where we can simplify a bit. So sine A times cos A, we would write as sine A cos A, plus, and then here, the cos A would cancel with that cos A, so we'd be left with sine A. Okay, over, and then on the bottom, we're actually not going to multiply that out. We're just going to keep it in brackets. If we multiply it out, we're going to have to expand it later, or factor it out later. Okay, so now we're back at step 1 again. So on in the numerator here, you'll notice that we have two terms and they have something in common. They have a sine A in common. So we're going to factor sine A out, which would leave cos A, divide it from the first term, left with cos A, plus sine A over sine A is 1. There we go. On the bottom, we have cos A and then 1 plus cos A. All right, that's looking pretty good. Oh, take a look. Look what's in the brackets. Cos A plus 1, 1 plus cos A. Are those the same? Yes, they are, because they're both positive. Doesn't matter the order then. So that factor can cancel with the one on top. And we are then left with sine A over cos A. Oh, I know that one. That sine A over cos A is tan A, right? Okay, we want it to look like the right-hand side. We want to keep in mind what's on the right-hand side too, right? So 1 over cotan A, if you recall, cotan A is 1 over tan A. So again, like we did on the last one, if we reciprocal the left side, we can reciprocal the right side. And therefore, tan A is actually 1 over cotan A. Yay, Yahoo, we did it. Okay, non-permissible values. Okay, so let's look at our original thing. Okay, there's the obvious can't divide by 0. Let's write those ones down. 1 plus cos A can't equal 0, and cotan A can't equal 0. Okay, then there's sneaky ones you have to look for. So tan, as we discovered here, was sine over cos. So again, I'll write this over here. Cos A can't equal 0. And any other sneaky ones? Cotan is cos over sine. Okay, so therefore sine can't equal 0 either. Oh, we got lots of restrictions happening here. Okay, so let's start with this first one. 1 plus cos A can't equal 0. So solve it like it was an equation. So we'd subtract the 1 to the other side. Then we're looking on our unit circle where cos, which is x, is negative 1. That would happen here. So therefore, A can't equal this one. Actually, we'll wait on the cannot equal. We're just going to put everything on unit circles so far, okay? In fact, I'm going to make this a little bigger. Okay, so far we have this particular terminal arm that can't happen. Okay, cotan. Cotan is x over y. In order for this to be true, x would have to be 0, whereas x0, that would be here and here. Okay, now next one, where is cos 0? Well, cos is x, so where is x 0? Got those already. So check. Okay, sine can't equal 0. Sine is y, where is y 0? Here and here. Got that one already. Okay, so look at this now. We've got all 4 of these. So that means we can start with the first one. A can't equal 0. How far apart are they? They're pi over 2 apart. Multiples, so multiply that by n. And there we go. We can get rid of the 0 if you like. There's our restrictions. Yay! Okay, we'll finish up the last example in the next video. Shouldn't be too long. We'll see you then.